Hello and welcome back to the video lecture series on statistics for machine learning. This is Amit Kumar Das and we are going through the estimation of parameters. As we have already seen that we try to estimate the value of a parameter, population parameter or a population characteristic, theta, from the value of the samples drawn. So the samples may be x1, x2 and so on and so forth. Okay, so in that in that regard, we can have point estimation and interval estimation. So we are going to now talk about interval estimation. So in the interval estimation, the basic premise is we have to find out two values T1 and T2, which give the lower and the upper boundaries of the confidence interval. And the confidence interval basically represents the interval within which the particular the parameter value is supposed to lie. Okay, so I'm talking about a parameter theta, say for example. So there is a confidence interval T1, T2. So I assume that the parameter value will lie within this confidence interval, and the confidence degree which I set is the basically the probability. The probability of what? The probability that theta is greater than equal to T1, which is the lower control limit, and less than equal to T2, which is the upper control limit, right? So this is what we try to figure out. Now, say for example, we are talking about the mean. Okay, so mean as the characteristic. So mean mu. Okay, so how do we do that? So say for example, we have already seen that if we talk about the sampling distribution of the sample mean, and the population is given to follow a normal distribution with a mean mu and standard deviation sigma. So n sigma, n mu sigma is the population. So we have seen that the sampling distribution of the sample mean is expected to follow also a normal distribution, and there is a estimate for the there is a formula that the mean is equal to mu and the standard deviation is equal to sigma by root over of n, where root over of n is the sample size, right? Now, if we try to convert this x into a standard normal variable, right? So how do I do that? We have already seen the example. So we have to x bar minus mu divided by the standard deviation. So sigma by root over of n. This is what we have to use, right? So this becomes the z, right? This is equivalent to the z. Now, this lies within the confidence limits. Okay, the confidence limits, let's set. So if I look at the z variate curve, right, and we know some standard values in the z variate curve, right, like z is equal to 0 is the midpoint, and between z is equal to minus 1.96 and plus 1.96. So z is equal to minus 1.96 and plus 1.96 plus. This whole area under the curve represents 95% or 0.95, right? So I can write it as P, uh, this whole thing, or which represents the Z, is greater than or equal to minus 1.96 and less than or equal to plus 1.96. This is equal to my 0.95. I call this the 95% confidence interval, right? Because 95% probability that this thing is going to fall within these values minus 1.96 and plus 1.96, right? So if I just transform it, the thing will become x bar plus minus x bar minus, so 1.96 into sigma by root over n, 1.96 into sigma by root over of n, okay, less than equal to mu, less than equal to x bar plus 1.96 into sigma by root over of n, right? So basically x minus sigma 1.96 sigma root over n, x plus. So the confidence interval now becomes, for this mu, the population mean, which is basically a parameter, is x bar plus minus 1.96 into sigma by root over of n, right? Where sigma is the population standard deviation. This is the 95% confidence interval. Okay. The same way I can also calculate the 99% confidence interval, right? Pretty much the same way. X bar plus minus 2.58 into sigma by root over of n. Now, like this, I can almost assume 100% confidence interval to be x bar plus minus 3 into sigma by root over n. This is a very important term in the statistical quality control or in statistics, right? This 3 sigma by root over n, x bar plus minus 3 sigma by root over n, because it is assumed that almost this whole area of the curve, this whole area under the curve, from here, from negative infinity to positive infinity, right? This whole area under the curve is going to be within the boundary z is equal to minus 3 to z equals to plus 3. Okay, there will be some tapering which will take some residual, very small amount of area, but that's kind of negligible. If we take the portion within minus 3 and plus 3, z equal to minus 3 and plus 3, that is going to be almost 100% the area under the curve. This is a very, very important thing in statistical quality control also. So by the way, so when we talk about the confidence intervals, these are the confidence intervals, right? So 95% confidence interval for mu is x bar plus minus 1.96 into sigma divided by root over n, and 99% confidence interval x bar plus minus 2.58 divided by into sigma by root over n, and 100% is basically x bar plus minus 3 sigma divided by root over of n. This is in a nutshell what we can talk about the confidence limits and the confidence intervals based on the different confidence, what should I say, confidence degrees. The confidence intervals do change. On 95% is something, for 99% this is another thing, and when we try to take almost 100% confidence degree, we have a different interval. Okay, confidence interval. Okay, so I think that's all about the interval estimation under the purview of estimation of parameters. So when we come back, we are going to talk more about the other thing, which is the test of hypothesis. So stay tuned. Thank you very much.